Hello, everyone. Welcome to our webinar. We started a little bit early today. I'm going to give people a couple of minutes to filter in here. Okay, it looks like we have some people joining us. I appreciate that. Welcome to APA's webinar titled Beam Me Up, Exploring the World of Engineered Wood Beams. My name is Mary Ewer, and I will serve as moderator for this session. Our speaker, Bob Cusick, and I both work for APA, the Engineered Wood Association. APA is a nonprofit trade association representing manufacturers of a variety of common structural engineered wood products. In addition to quality verification and product testing, APA conducts research to improve engineered wood construction systems and educates users and specifiers on the product's proper use and potential applications. Before we start today's webinar, I want to cover a couple of housekeeping details. Bob's presentation will last about 50 minutes. A handout showing the slides can be found in your GoToWebinar dashboard. To ensure that everyone can hear clearly, we have muted all participants. We do encourage you to submit questions by typing them into the questions pane on the control panel on your screen. I will be monitoring those throughout the session, so please make sure you're sending them to organizers and panelists. We will have time for some Q&A at the end of the session, and we'll get through as many questions as we can. I'd also like to note that today's webinar is approved for AIA and ICC continuing education credits. About an hour after the conclusion of the webinar, an email will be sent to each attendee. It will include a link where you can get customized AIA and ICC certificates of completion. Our presenter today is Bob Cusick, Engineered Wood Specialist for APA based in New Jersey. In his role, Bob works with designers, building officials, and builders on the various engineered wood products that are used in buildings today and consults on engineered wood use in construction applications. Prior to joining APA, Bob spent 20 years as an engineer providing technical support for a major manufacturer of engineered wood products. He's a professional engineer, licensed in 9 states, and received his Bachelor of Civil Engineering from Villanova University and a Master of Civil Engineering from the University of Delaware. For those of you just joining us, welcome to APA's webinar on the topic of engineered wood beams. I will now turn the microphone over to our speaker, Bob Cusick.
Thank you, Mary. As Mary mentioned, today's topic is Beam Me Up, Exploring the World of Engineered Wood Beams. This program will present the different types of engineered wood beam products available today with a primary focus on glulam and structural composite lumber. We will review the proper design and specification in accordance with the International Building Code, explore new technologies, streamline design options and sustainability issues, and review the constructability benefits of engineered wood beams. Today's presentation's objectives are to understand engineered lumber product basics, review the different characteristics of the various structural composite lumber and glulam materials available to be used as beams. We'll look at various constructability aspects of these beam materials, present the guidance on the proper design and specification of SCL and glulam beam products. A quick look at our agenda today. I mentioned the presentation will review sustainability of engineered wood, product basics review, introduce new technologies, explore constructability, review proper design and specification of engineered lumber products. Here's what the manufacturing process for wood looks like. Trees use the energy from the sun to grow and grow, and then they're converted into wood products. It's simple and environmentally friendly. Today, we're using second and even third generation trees to make wood products. After harvest, trees are replanted and can be used again. In the 1920s was a low point in forested areas in the United States. However, today there are more than 40 million more acres than there were back in the 1920s. I'd like to emphasize that 70 to 90% of our forests are natural, not planted. Using trees for building products also offsets the need for using some other building products, which are likely not to be from a renewable or sustainable source material. Since the sun is going to shine anyway, we might as well take use of its energy and grow more trees to use. I'd like to point out that there are 2 webinars available on APA's webpage specifically dedicated to wood as sustainable building material. I would encourage, if you are interested for more on this topic, to review them. Let's briefly talk about some basics regarding wood strength so we understand how that wood is reassembled to make an engineered wood product. Wood is primarily made from parallel tubular structures. It's best to think of the grain of the wood as being similar to a bundle of straws. So when the compression or tension is applied parallel to the grain or along the length of the straws, the bundle is strong and efficiently resists crushing or pulling apart through tension. If the load is applied perpendicular to the length of the straws or perpendicular to the grain, the straws can crush more easily, or they can split if notches or loads are applied in a manner that wants to pull the straws apart. This illustrates the anisotropic nature of wood, which is different strength properties in different directions. Engineered wood can be described as any wood-based building material that has been improved physically by a man-made process. We essentially take the tree apart, sort out the flaws, grade the wood, and then engineer and reassemble the wood, orienting the grain so the finished product takes advantage of wood strength properties. Today we'll be talking about a group of structural wood products manufactured using either veneers, wood strands, and solid wood that are commonly used as beams and columns. These engineered wood products fall into 2 main categories that we're going to discuss today: laminated timber, or glulam, and structural composite lumber that consists of a family of products like laminated veneer lumber, oriented strand lumber, laminated strand lumber, and parallel strand lumber. All of these names and acronyms may seem a little bit confusing, but hopefully we're going to clear the fog on that a little bit today. So why do we use engineered wood products? In addition to being a green, sustainable product, engineered wood products provide a uniform, predictable performance, uniform weight, and strength. These products are quick and easy to install using the same practices that framers have been accustomed to with dimension lumber. These products are engineered to maximize strength for an application, be more dimensionally stable than dimension lumber, and provide an efficient use of our wood fibers in a way these products are manufactured. So let's begin by reviewing the product basics, starting with structural composite lumber, or SCL. SCL refers to a class of wood products composed of veneers or strands oriented in a manner to maximize strength and minimize the natural flaws that can exist in lumber. Structural composite lumber outperforms dimension lumber when either face or edge loaded. They're manufactured and sawn to consistent sizes that make framing more consistent and easy. SCL strength properties are published on a proprietary basis by the manufacturer and recognized in their code evaluation reports. Laminated veneer lumber, or LVL, is the most widely used type of structural composite lumber. It uses specially selected, ultrasonically graded, kiln-dried veneers and orients all of the veneers with the grain running lengthwise. The veneers are lap joined to create long lengths. LVL is commonly used for beams, headers, rafters, scaffold planking, as well as I-joist flanges and studs. Parallel strand lumber, or PSL, is also manufactured from veneers, but they're clipped into long strands and bonds together in a parallel formation. By using the strands, you can get better utilization out of the log, where full veneers have inconsistencies like knots, bare, wane, and voids. It's often found at the beginning and end of each log's veneer sheet, and it would not be suitable for LVL. But like LVL, the grain is running in the direction of the length of the beam member to maximize the bending strength. Strands are cut into lengths that are around 300 times their thickness, or approximately 1/8 of an inch thick by 1 inch wide, 3 to 4 feet long. This product also commonly uses headers, beams, and columns. At this time, this product is a proprietary product available from one manufacturer. LSL, or laminated strand lumber, is another member of structural composite lumber family used primarily for beams, headers, studs, rim boards, and stair stringers. Unlike PSL, the strands are not cut from veneers. Rather, this product is typically made from smaller diameter trees consisting of a mix of hardwoods like harvested aspen, poplar, and maple, and the logs are stranded instead of planed into veneers. The length to thickness ratio is around 151, so these strands are typically around 1/8 of an inch by 1 inch wide by approximately 12 inches long. OSL, or oriented strand lumber, is another member of the structural composite lumber family that is also commonly used for beams, headers, studs, rim boards, and sometimes millwork. Similar to LSL, the strands are not cut from veneers, but use smaller strands than their LSL cousin. The length to thickness ratio for OSL is around 75 to 1, so strands are typically 1/8 of an inch by 1 inch wide by approximately 6 to 7 inches long. As I mentioned, structural composite lumber is proprietary, where the design properties are maintained and published by the manufacturer of these materials. Glulam is a little different in that glulam design properties are consistent across manufacturers, and they're produced in accordance with the ANSI A190.1 standard. Glulam consists of wood laminations bonded together with the wood grain running parallel to the length of the member to align these plies in a manner to achieve the greatest strength for the product. Although you can get glulam in nearly any depth and you're only limited in length by the manufacturing and transportation, beams carried by your local dealer usually don't exceed about 18 inches in depth. They're commonly used as purlins, ridge beams, floor beams, headers, and columns. Typical width of a glulam ranges from 2.5 inches to 10 3/4 inches and is commonly manufactured from southern pine or Douglas fir. As I mentioned in the previous slide, glulams do not have the same strength properties throughout the depth of the member, so they varies a bit. But like structural composite lumber, where the wood grains are aligned to produce the greatest strength, glulam beams also align the wood fibers in the long direction, but they have the unique ability to place the best material where it is needed most to get the most strength out of the beam. If we consider a balanced layout, as shown on the left, the beam has equal capacity in both positive and negative bending and is primarily used in continuous beams or long cantilevers. As it is unknown how stock glulam beams will be loaded, they are generally balanced beams, so that's what you'll find at your lumber yards. Looking at the layout on the right of an unbalanced beam, they have unequal capacity in the positive and negative bending and are primarily used in simple beams or short cantilevers. Because of this unequal capacity, unbalanced beams have a unique top and bottom and must be installed correctly. In response to the high stiffness that was being produced by some structural composite lumber manufacturers, glulam manufacturers developed a high-strength glulam beam that married traditional solid sawn plies with high-strength LVL located in the outer plies, giving us the best of both the glulam and the LVL worlds. Hybrid beams use LVL top and bottom laminations to increase the tensile strength. It not only increases the strength of a traditional 24F 1.8E beam, but is now one of the strongest beams available in the market with values of 30F 2.1E stiffness values. Although not available as a stock item, they do come in conventional glulam depths as well as an I-joist compatible depth to fit well within today's engineered wood floor systems. With respect to columns and truss cords, due to the potential of loading on all axes, the glulam layup utilizes the same grade throughout the member because stresses are distributed equally. These members do have some bending capability as well, but are used primarily in tension or compression parallel to grain or the long axis of the member. Glulam beams are also available in different appearance classifications as noted in APA Technical Note, Glulam Appearance Classification for construction applications. But to reiterate, the line of distinction between generally stocked beams by your dealer and those that might be used for exposed aesthetics. For use as beams and headers where beams may be hidden, you're likely to be comparing glulam against other engineered wood beams and headers. You'll be dealing with a framing or an industrial appearance classification. Glulam can be produced in curved shapes and is available in a range of appearance characteristics to meet the end use requirements. In addition to being available as curved members, glulams are also available in long lengths greater than 100 feet. Here we see a beam in the top right photo that measures 10 3/4 inches by 72 inches deep with a 115-foot clear span that is installed at the Oceans exhibit at the Indianapolis Zoo. As you saw in the previous slides, glulam beams can be ordered as a curved member for dramatic architectural effects, but they can also be ordered with a camber so that under dead loads the beam is flat. This is desirable for long beams such as ridge beams where the design professional will specify a specific amount of camber for these members to eliminate sagging. Beams ordered with camber, like unbalanced beams, also have a unique top and bottom, and this will be noted on the beam. However, stock beam camber is not an issue as they have little or no camber and are nearly flat. When manufacturing tolerances are considered, the difference between a cambered stock beam and a flat beam becomes less apparent. There's a common misconception that all glulam beams are cambered and can create a hump in the floor. I really just wanted to highlight that this is not the case with stock beams, and they can be used in similar applications as structural composite lumber. As I mentioned, glulam beams typically come in widths ranging from 2.5 inches to 10 3/4, but that doesn't prevent the manufacturer of wider glulam beams. Here's an example of a 21-inch wide by 27-inch deep by 110-foot long glulam. This is actually a column. You can see in the photo that there are multiple plies in each layer in the makeup of this member. In addition to the multiple plies per layer, we can also see where a conduit was run through the length of the member. Interesting fact is this member was actually used as a column that served as the trunk of a palm tree cell tower. While it is clear that you can do some exceptional designs with glulam beams, we're going to focus on the more mundane typical issues, with standard beams and headers today. While all these products can be used as ridge or ceiling beams, how the beam is exposed will influence your beam choice. All these beam products could be suitable if the beam is not exposed, buried in an attic, or wrapped with create a faux wood finish, for example. On the other hand, if an exposed beam is desired, an architectural or better grade of glulam can be used, or even some structural composite lumber has good wood characteristics that many people like, and they will leave those exposed as well. These beams can be stained and coated to bring out the beauty of the wood. Notice the ceiling fan hanging from the beam. We'll talk about that a little more in a bit. In basements or crawl spaces, beams can be either dropped or installed flush with the joist framing and left exposed. In basements, drop beams allow for an easier installation of the floor joists. Especially if I-joists are used, they can be installed on a multi-span application over the beam. In addition, these beams, being available on long lengths and multiple widths and depths, can be used to improve the floor performance compared with dimension lumber beams, which would be limited to shorter spans, although they need to be spliced. Structural composite lumber and stock glulam beams are both suitable for basement or crawl space applications. In finished rooms, SCL and stock glulam beams would be acceptable if concealed, or an improved appearance grade glulam may be used if the beauty of the exposed wood is desired by the homeowner. Here you can see a typical header for the garage door and an exposed floor beam in the center of the garage. As you see in this situation, the appearance isn't paramount to the end use of the beam. Therefore, a framing classification or industrial classification for this glulam beam can be used. As mentioned earlier, beam headers are available in lengths that will allow extensions on each end of the garage or window opening to help builders meet code where there's a little bracing on either side of the opening to create a portal frame. Also note that the beams used for garage door headers or even APA's narrow wall bracing method in a wall, a 2-ply LVL at 3.5 inches wide fits nicely in a 2x4 wall, and glulam beams available in 5.5-inch widths will fit nicely within a 2x6 wall. By selecting a beam that matches the depth of the wall, we can minimize furring that would otherwise be required for the connections on both sides with the APA narrow wall bracing method with a panel connection on the front and a strap on the back of the beam. Glulam and some SCL products are available to use as columns, either as a standalone member or within the wall framing. Glulam and SCL columns are easy to install and lightweight alternatives to steel for floor framing support. Wood-to-wood connections are also very framer-friendly, and most can easily be finished or wrapped with gypsum if required to achieve a fire rating. Columns are also stocked at the local dealer and readily available. These columns can be useful in the basement or any of the upper floor stories when compatibility and workability are important to the framer. Stock glulam columns are available in multiple sizes ranging from 3 1/8 to 8 3/4, including the common construction sizes of 3.5 and 5.5 to match other lumber framing materials. SCL columns are typically available in 3.5, 5 1/4, and 7-inch widths. So far, we've mostly talked about how glulam and SCL beams frame within a wall system, where glulam beams often match the wall width. As engineered wood floors became popular, it was important for all beam manufacturers to be able to offer products that would be compatible with I-joist steps for ease of framing and finish, because some of the I-joist steps are a little different. Since I-joist manufacturers also manufactured SCL, there was a natural alignment with the joist depth offerings. However, I-joist compatible glulams to match I-joist depths were later developed and are readily available in all markets today. Because of their availability in long lengths, glulam or SCL columns and studs can be used to frame multi-story wall systems to add both strength for the wall and ease of construction for the builder. I recommend you contact the manufacturer of these systems for specific design and specifying information. Some common applications, however, would be for great rooms and foyers of residential construction, with walls over 10 feet. This is needed when both vertical and perpendicular loads are equally important in the design of these walls, when wind loads need to be considered. With long studs and columns, there's no hinge connection in the middle of the wall, so there's no loss of strength. Glulam and SCL attributes are perfect for resisting wind pressures and associated deflection perpendicular to the wall. Both glulam and structural composite lumber is available in 2x4 and 2x6 standard wall framing depths. Let's just take a brief moment and look at some new technologies that we're starting to see on the market. Cross-laminated timber, or CLT, is a versatile product that in many ways can be considered a wide beam or a panel with strength in two directions, where they can be used for floors and walls. Cross-laminated timber is a large-scale, prefabricated, solid engineered wood panel. Lightweight, yet very strong, with superior acoustic, fire, and thermal performance, CLT is also fast and easy to install, generating almost no waste on site. CLT also offers design flexibility and low environmental impacts. For these reasons, cross-laminated timber is proving to be a highly advantageous alternative to conventional materials like concrete, masonry, or steel, especially in multifamily and commercial construction. A CLT panel consists of several layers of kiln-dried lumber boards, typically stacked in alternating directions, bonded with structural adhesives, and pressed to form a solid, straight, rectangular panel. CLT panels consist of an odd number of layers, usually 3 to 7, and they may be sanded and pre-finished before shipping. While at the mill, CLT panels are cut to size, including door and window openings, with state-of-the-art computer-controlled routers, capable of making complex cuts with high precision. Finished CLT panels are exceptionally stiff, strong, and stable, handling load transfer on all sides. Interest in using engineered wood products in Type 3 and Type 4 construction has been rising in recent years. The wood industry has been heavily engaged in the promotion of multifamily and light commercial construction in Type 3 and Type 4 buildings. Type 3 and Type 4 construction is that type of construction in which the exterior walls are of non-combustible materials, except that fire-retardant treated wood framing is permitted within the exterior wall assembly if it's 2-hour rating or less. To address this opportunity, APA, in cooperation with the USDA Forest Products Laboratory, worked to develop ASTM standards for the evaluation of FRT glulam and LVL. Recently, APA published a technical note summarizing the results of this pilot test program examining the structural properties of FRT glulam. For structural design, the actual treatment and hygrothermal effect on the glulam properties need to be obtained from the treater who provides the fire-retarded treatment. Additional research on fire-retarded treatment for LVL is still ongoing. Girder versus beam versus header. So what is the difference? It's really not much. Generally, girders are considered to carry the heaviest loads and have long spans. Beams are often flush in the floor and may carry load to the girder, so they're kind of a smaller cousin of the girder. Headers are simply beams that are installed within the plane of the wall to frame an opening. Typically, headers are supported by jack studs and may carry load down to a beam, a girder, or directly to the foundation. Pictured on the right is an LVL beam that frames into a glulam girder. The center photo shows a long span girder. And the photo on the left shows an LVL header being used in a portal frame application, where it extends over the sidewalls. The variety of sizes and strength available with glulam and SCL products allow the specifier to select the right beam for the application. The choice of a build-up beam versus a single beam will depend on the contractor, but each has its advantages. Build-up beams can be easier to handle and fasten in place. This is especially advantageous in renovation work, where beams may be hard to get into place due to existing additions. The downside is needing to design and install these connections to transfer the load to all of these members. Solid members, on the other hand, are heavier to handle, harder to handle, but they do eliminate the fasteners, and they may require less lateral bracing along the length of the member. Many don't realize this, but it is acceptable to cut holes in both structural composite lumber and glulam beams. Cutting holes in LVL is pretty straightforward, as shown here. For uniformly loaded beams, small holes up to 2 inches in diameter can be cut through the middle third and height, middle third of the length, height and middle third of the length of the beam. By cutting in this area, we're locating the holes away from supports where the shear is lower and away from the beam edges, so we minimize the impact on the allowable moment of the beam. Holes are also permitted in PSL and LSL. However, because of the stranding and orientation of the strands, they may have different hole cutting guidelines than we're showing here with LVL. So we'd recommend that you reach out to the manufacturer of those products for any additional hole cutting guidelines. APA does have a tech note on field notching and drilling of laminated veneer lumber that provides general recommendations for cutting holes in LVL. For more detail, you can also refer to the manufacturer's instructions, particularly in regard to cutting and notching of PSL and LSL. For horizontal holes and glulam beams, different criteria exist and is detailed in APA Technical Note, Field Notching and Drilling of Glued Laminated Timber Beams. Holes should be in areas that are 50% of design for bending moment or at the ends close to bearing. There should also be at least 2.5 times the hole diameter of wood remaining on either side of the hole. There are 4 basic criteria for horizontal holes in this literature piece. The hole diameter should be the smaller of 1.5 inches or 1/10 of the beam depth. The hole location needs to be at least 4 hole diameters from the top or bottom edge of the beam and 8 hole diameters from either end of the beam. Hole spacing should be at least 8 hole diameters from the next closest hole, measured by the largest hole diameter of the two. The number of holes should not exceed 1 hole per 5 feet. So for example, in a 20-foot beam, you would be able to cut 4 holes. This slide shows the hole zones for 1 inch or smaller diameter horizontal holes. These holes are permitted in a uniformly loaded simple or multiple span glulam beam greater than 7¼ inches in depth. The small hole guidelines we recently reviewed are permitted for all beam applications. There's no engineering analysis required generally. Recently, however, APA's Technical Service Division has done research on larger holes in both LVL and glulam beams. This research allows for large holes up to 2/3 the depth of the beam and requires engineering analysis. Additional information on these large holes in LVL and glulam can be found on the APA technical notes for glulam and LVL as shown on the slide on APA's web pages. Remember that ceiling fan. Whenever possible, it is best to avoid drilling vertical holes through glulam and structural composite lumber beams. When vertical holes are drilled through LVL, the LVL should be a minimum of 3 inches wide solid member and not a built-up LVL beam. Vertical holes drilled through the depth of a beam causes a reduction in the capacity at that location directly proportional to the ratio of 1.5 times the diameter of the hole to the beam width. For example, a 6 3/4 wide glulam beam with a 1 inch vertical hole drilled through the beam will see a reduction in moment allowable of 22%, leaving the beam with about 78% of its original strength. This picture needs little explanation. So how many issues can we see here? Excessive notching, holes too close together, holes too close to support, quality electrical work, hard to say. This picture also needs little explanation, but does raise a couple questions. What is the depth of the notch in this LVL? We observe where the card is inserted in the saw curve. Of course, a better question might be why weren't the cripple studs just shortened a bit instead of notching this beam? Additional information can be found in APA's technical note, Field Notching and Drilling of Laminated Veneer Lumber, which provides additional information on the field notching of LVL beams. When the bottom of the beam is notched, particularly at the end where the shear is the greatest, the beam wants to split. Recall how we discussed that the wood fibers are similar to straws. We can see in the photo on the left that the straws want to split apart at the bearing. Tension side notches are limited to 10% of the depth of the beam. If a glulam is notched, it is possible that a reinforcement can be designed. As I mentioned, the depth of the notch can't be deeper than 1/10 of the beam depth or more than 3 inches total. A lag screw can be drilled and screwed into the upper half above the neutral axis of the beam. The size and location of the lag screw will have to be determined by a design professional. This is the same fix that can be used if a significant split has developed on the tension side of an uncut beam. Also, if a beam is notched, the corner should be pre-drilled with a 1/2 inch radius to relieve the stresses caused that you would get at a 90-degree cut corner. You remember that unbalanced beams are designed with different bending stresses for their top and bottom laminations. The word top, as I mentioned, along with the APA trademark, is clearly stamped on unbalanced beams. But what do you do when you see this when you visit the job site? Some will say top on the bottom means turn it over, please. But in reality, that may not be possible. The designer of record will need to evaluate or re-engineer the member. Keep in mind that in addition to the unbalanced beam we discussed, camber beams also have a top and bottom. So you need to look at this. An unbalanced beam does have a capacity that can be checked. It loses about 25% to 30% of its moment capacity, and it has the ability to be reinforced if needed. Whereas a cambered beam will already be deflecting downward and is much more difficult to correct. Let's take a look at some strategies for durable construction. One of the best advice we could give related to all wood construction is keep the beams dry and focus on the proper design and construction details and moisture management. Use an appropriate preservative treatment when the wood products are exposed to the elements, or consider a naturally durable and decay-resistant wood species when designing the structure. Remember that worldwide there are numerous examples of wood structures that have been in use for 50 to 100 years. The photos on the right show homes constructed over 100 years ago that have endured because of good detailing related to moisture management. Exposed applications present a unique challenge for wood products. Depending on the use category, exposed beams and columns would need to either be of a naturally durable wood species or be a preservative treated wood product. The building code generally tells you where treated or naturally durable materials are needed, and this includes where you have contact with ground or directly with water, contact with concrete, or where the wood is within 12 inches of ground for beams or 16 inches of ground for joists. When floor framing is in termite zones, there might be protection, typical in Hawaii. When used below the design flood elevation, you may need to treat a product. And when the in-service drying isn't readily available, an expected moisture content will be over 19%. So while these requirements are good, in knowing that the materials need to be treated, the building code doesn't specify how aggressive or what type of treatment to use for these different applications. To kind of fill out this detail, the American Wood Protection Association developed a use category system. This standard divides into 5 main use categories for durability, ranging from use category 1, which is an interior dry use application, to use category 4, which is a heavy marine use classification. The use categories that I'd like to focus on today are use categories 1 through 4, as these are the main categories where treated glulam or SEL would be used. Note that these categories 3 and 4 are also broken down into more specific uses. Starting with moisture category 1 is your basic interior dry moisture content use application, less than 16%, so no treatments required for use category 1. Use category 2 is where you would first see the standard where we need some treated product. These products are not in contact with the ground, but they may be subject to dampness. One SCL product that has been treated for this application is LSL treated with a zinc borate. It protects against termites and fungal decay. But note that the borate will leach out with continued wetting and drying, which is primarily why this is approved for this use category. There's not a lot of wetting and drying happening here. Some common uses for the treated LSL would be sill plates or beams that are bearing directly on concrete or masonry. Let's take a look at use category 3, which we mentioned was divided into 2 categories: above ground protected and above ground exposed. So that's exposure to your rain. And then we'll also look at use category 4, which is divided into 3 categories, as these are the applications where we're going to commonly see treated glulam or SEL specified. PSL is marketed with 2 treating options, with their beam products being treated with copper azole for a use category 4A standard, and their column products are treated with CCA for a use category 4B standard. LVL is available for use in exterior construction above ground applications rated as use category 3B. Stock glulam beams generally offer more options and are also treated with different treatment chemicals for the different use categories. Use category 3B, 4A, 4B, and 4C are available in glulam. Note that beams can be used in categories lower than the use category for what the product was treated. I recommend you review your applications or reach out to product manufacturer for additional information, or you can reference APA's publication, Preservative Treatment of Glue Laminated Timber, that provides information on the AWPA use categories and the available treatments. In addition to treated materials, designs can also be done with naturally durable wood species like Port Orford cedar, Alaska yellow cedar, western red cedar, and California redwood. These product choices provide aesthetically pleasing and environmentally alternative to treated products and are available in glulam beams and columns. The designer, when specifying these species, should recognize the different design values for these products and should be specified accordingly on the design drawings. I'd like to point out an interesting case study involving the use of Alaskan yellow cedar was the cover for the Santa Maria Water Reservoir in Santa Maria, California. When the city of Santa Maria added a new 7 million gallon reservoir in 2001, a roof cover was needed. Their existing reservoirs were covered with open web trusses with treated lumber. It was decided at this time that, considering current environmental constraints, that this was no longer viable for applications over drinking water. So the heartwood of Alaska yellow cedar, with its naturally resistance to decay and longevity, was a clear choice for framing members. The roof was constructed using Alaska yellow cedar glulam members with beams up to 8.5 inches wide by 25.5 inches deep, with the longest beam being 62.5 feet, spanning a 56-foot opening. From a construction standpoint, the glulam offered another benefit. There was a time savings associated with this. If the project had been constructed with open web trusses that used dimension lumber for the cords, the lead time to source materials in the size needed would have stretched into months. The glulam provided an environmentally friendly alternative, allowing the use of wood from smaller diameter trees to form the framing members, and the project was completed on time and $50,000 under budget. Whether they are treated or not, checking of beams can occur. The question is it a structural concern? APA provides guidance in reviewing checks in glulam. Checks in other structural composite lumber products should be reviewed with the manufacturer. Let's briefly talk about how wood reacts to moisture. First, wood swells or shrinks as it gains or loses moisture in response to changing relative humidity, and to a far lesser degree, temperature in the surrounding environment. If the difference in moisture level between the core and surface of the wood becomes great enough, the internal stresses associated with these dimensional changes can induce tensile stresses perpendicular to the grain. These stresses can result in seasoning checks developed across annual growth rings. This is most common in solid sawn lumber beams. Dimensional changes also need to be understood with respect to moisture changes. Exposure to weather and sun will increase the amount of checking in all wood products. Checks should not be confused with delamination. Wood lamination and glulam have moisture contents limited to 16% and is typically well below this value at the time of manufacture, which results in fewer seasoning checks. These checks are noted by the presence of torn fibers and should not be confused with the failure of the adhesive, known as delamination, where the small lamination surface is seen within the wood fiber tear. Such checks are seldom a structural concern, but do impact the aesthetics of the beam. To reduce the opportunities for checking to occur, it's best to install glulam in environments with consistent humidity levels and control the moisture content of the product by protecting the wood from high moisture areas such as concrete or refrigeration, and thoroughly seal the beams on all 6 surfaces. I'll note that checking is a natural phenomenon associated with the natural drying of the wood, whereas delamination is a deterioration of the glue bond when exposed to moisture. With the introduction of wet use adhesives, moisture-based delamination was eliminated in the United States. This was assured in the glulam standard by requiring adhesives to meet ASTM standard D2559 for adhesives for bonded structural wood products for use under exterior exposure conditions. If the checking in the beams does become a concern, you can refer to APA's technical note, Evaluation of Check Size in Glued Laminated Timber Beams. I'll walk you through a little bit of that document, but a quick review of some of the common checks you may see. The first being end checks, which originate and generally stay in the location of the end of the member. If an end check has a length of less than half the depth of the member, there is no concern. I like to point out that the difference between a check and a split is that a split is a separation the full width of the member. Many times people confuse a split with a check. Second type is a side check, where the opening is parallel along the side face of the member. If a side check is no greater than 1/3 the width and 1/3 the length, there really should be no concern. The third type is a bottom check that occurs on the bottom face of the member. As long as the check remains parallel to the grain, these can be of any length and not pose a structural concern, even if full length. I tend to think of this as my multiply application. Let's look at some basic design concepts and considerations in designing and selecting a beam. The designer will need to think about the type of member they would like to use, determine the allowable design stress or layout selection by the type of member chosen, develop the load to be carried by the member, and perform a structural analysis on the selected member. Remember to apply appropriate stress modification factors for the product and identify any special design considerations. Lastly, and most importantly, connection design in detail. APA has additional information on connection design in a separate presentation. I'm not going to really delve into that a whole lot in this presentation. Let's look at the types of members. We already reviewed the different glulam and SCL materials, but there are many considerations in the proper design and specification of a beam. This includes proprietary versus non-proprietary, product availability, availability of software or literature tools that help ease design of the structure, and the affordability. Proprietary members are limited to a single manufacturer. Because of this, it may require design time when a substitution is requested, and a reference code report will need to be updated with code changes. Examples of proprietary members are our SCL family of LVL, LSL, OSL, and PSL. Non-proprietary products are designed for a performance standard. This creates room for competition and allows the contractor to choose the most cost-effective and readily available product, since this also allows for easy substitution across manufacturers of the different products. Examples of non-proprietary products are dimension lumber and glulam beams. Let's take a look at SCL glulam and select structural lumber and compare the strength properties that mostly control beam design, that allowable bearing stress, and the modulus elasticity. This relates to the stiffness of the material or the ability to resist deflection. Looking at this table, we can group these materials into three categories based on their stiffness. We see that LVL and glulam offers products that fit into all categories, whereas LSL and dimension lumber fall within a lower medium to strength range. LVL, glulam, and PSL can be reduced with properties that fall within the high strength ranges. Comparison with some commonly specified sawn lumber grades show how these products compare with these grades and how substitution of glulam or SCL could be substituted for similarly sized specified sawn lumber products. But keep in mind that while this type of substitution is technically acceptable, the member design for the actual conditions using product-specific tables or software could result in a more economical option. Let's take a look at what glulam combination symbols are and how they are reflected in the APA glulam trademark. The glulam trademark identifies the allowable stress of the material, the appearance classification, how the plies are graded, visually or mechanically, the stress combination number, and the wood species. That's a lot of information, which leads to the question, what is important to specify in a glulam beam? It sounds very complicated. It really isn't. I would emphasize that while many stress classes are listed in codes, that you focus on a 24F 1.8E or a 30F 2.1E beam, as they are the most commonly stocked material. I recommend you specify the allowable design stress and not worry about all the specific layout detail. So to simplify specification, we would have a table that looked like this, where the design values are listed for the different stress classes. This layout is very similar to what you would see with structural composite lumber and dimension lumber. With a closer look at the APA glulam grade stamp or trademark, we see that it contains several critical pieces of information, and you should know what they are when you specify the beams. Suppliers can assist their customers in understanding the information on a grade stamp. Also, you can refer to APA's glulam product guide for more information on glulam specifications. Design of glulam beams can be done using basic engineering mechanics, using allowable stress design as detailed in the National Design Specification for Wood Construction. The design values for glulam is consistent between manufacturers, produced in accordance with ANSI A190.1 and is published in ANSI 117. And this is included in a separate NDS supplement publication. Since product design values are consistent across manufacturers, APA is able to support design-based literature for glulams, in addition to standalone literature for the glulam manufacturers. So this includes our APA glulam floor beam guide that has tables that lay out different tributary wefts that can be cross-referenced against the column or support span, allowing the designer to select an appropriate floor beam. In addition to these tables, this guide also provides relevant details to assist in the installation of glulam beams in a floor application. APA's glulam garage door headers Also provides tables to allow for the selection of an appropriately sized glulam beam over garage door for different width openings. Glulam beams make an excellent garage door header and can easily be used in portal frame applications. APA's substitution of glulam beams for steel or solid sawn lumber provides guidance to assist in the substitution of glulam beams for steel or solid lumber. This publication guides the specifier to select glue-laminated timber beams of equal or greater strength and stiffness that can be often substituted for saw lumber or steel beams that may be sized through accepted other published span tables or for these products that are published in the IRC. I would like to point out that the 2018 NDS provides a procedure for designing exposed wood members for fire resistance, which is applicable for glulam beams. This methodology will require additional outer tension laminations be substituted for a core lamination on the tension side for unbalanced beam and on both sides for a balanced beam. Similar to glulam, structural composite lumber, including LVL, LSL, and PSL, can be done using basic engineering mechanics in Section 8 of the National Design Specification for Wood Construction. This section indicates that the design value shall be obtained from the structural composite lumber manufacturers' literatures or their code evaluation reports. I'd like to take a little minute and mention a word about the modulus of elasticity, or E, in comparing products, where E is the measure of deflection resistance that a beam or header provides. Apparent or shear-free E has caused confusion with designers, so I hope I'd like to clear things up a little bit. In wood design, there are two deflections to be considered when designing a member: a deflection based on bending of the beam plus the shear deflection. This is represented with the two-term equation shown here, equation 1. However, for prismatic bending members, the shear deflection under design load is generally small compared to the bending deflection. So for simplicity and practicality, it is customary to use the apparent modulus of elasticity for the calculation as shown here in the one-term equation, equation 2. It should be noted that the relationship between apparent E and true E depends on the span, moment of inertia, and the shear deflection coefficient. Some manufacturers categorize their tabular values as apparent E and some as shear-free E. To equate apparent E and shear-free E, the apparent E value is reduced by approximately 5%, and the appropriate one-term or two-term equation is used. This is where some confusion can be introduced, as some SCL manufacturers categorize their tabular values as apparent E and some as true E. This can make substitution of products challenging, and that you need to know which E is being used by each manufacturer. I find the easiest way to tell which E is being used is look at the literature and look at the deflection equations they have in the literature or the code reports. Can a product be published with a true E value of 2? Can a product with a published true E of 2 be substituted for a product using an apparent E of 2? Maybe not. If designers are using the one-term equation for apparent E and don't realize that the published value is true E, the design can be non-conservative when deflection governs the structural design. Looking at the table, we see that a true E value of 2.0 equates to an apparent E of 1.9. So a more detailed analysis will be needed to see if this substitution is acceptable. For further discussion, APA has a technical topic, true and apparent E, parent moduli of elasticity, that you can review. However, unlike glue laminated beams, the design values for SCL, as I noted previously, are provided by the manufacturer and will be different from manufacturer to manufacturer. The major reason for different values is that LVL is produced across the United States using different wood species based on what wood basket they are being produced. Example, LVL can be produced with southern pine, Doug fir, yellow poplar. Some manufacturers will offer a West Coast Doug fir version and an East Coast southern pine version. Some may publish the lowest design value from the different wood species, providing only one set of design values across the United States. We're going to discuss why it is important to get the information correct in the specification. Structural composite lumber is often specified by its manufacturer's brand name, E value, and the bending stress value F sub B. We reviewed design values from 7 LVL manufacturers. One manufacturer publishes different values for eastern states than western. While all 7 promote a 2.0 E product, we can see where confusion immediately comes into play as we compare to the manufacturers that publish apparent E values. 4 of the manufacturers publish a true E, while the other 3 publish an apparent E. The published bending stresses range from 2600 to 3300 psi. The allowable stresses in the other directions can be seen here as well. I may consider that if I design a beam assuming manufacturer 1 who publishes a true E, it will compare with other manufacturers that published a true E and is conservative, and compared to manufacturers that publish an apparent E. As you can see, this can get quite confusing. So what do we do? How do we specify structural composite lumber? It's not a problem. The only difference is the APA doesn't publish load tables similar to what we have reviewed for glulam. However, each SCL manufacturer generally has similar load tables for their products based on their code reports. Some manufacturers' load tables are similar to what I presented for glulam, but may provide a PLF or pallets per linear foot table. This table is a little different than selecting the beam based on a tributary width. With these tables, both live load and total load, including dead load, would be determined based on a tributary width, would include multiple floors and partition loads if appropriate. The designer can then select an appropriate beam by looking up the span to determine which beam works best for the live and total load PLF. That was determined using the appropriate load duration factors, whether the beam is in a floor or roof application. Additionally, glulam or SCL beams can be sized using glulam manufacturers or third-party software. Based on a survey, we found many engineers default to spreadsheets and proprietary beam design software. However, they also confirmed that they have one or more of the following programs, either EnterCalc, RAM, or RISA, which has more comprehensive beam design functionality for glulams and SCL manufacturers. The tendency to use manufacturers' proprietary software that they're used to is certainly giving a specific edge to that manufacturer. Many retailers stock glulam and SCL sizes, but the manufacturer's brand may drive what specific SCL products they have in inventory. However, SCL and glulam manufacturers are typically associated with a wholesale distribution network that makes product, including less commonly sizes, readily available. For some products, when specifying SCL, it may be beneficial to talk to the builder about a manufacturer or dealer preference that you can specify the desired manufacturer-specific product for the job. The challenge is specifying for projects where the builder plans to bid the project between different dealers and manufacturers, as this typically where substitution requests will be submitted and need to be evaluated. The specification of brand X, equal or better, presents a substitution challenge when comparing design values. It is best to find out what products are readily available in the market, whether from retailers or from local lumber distributors where the project is going to be constructed. Glulam is often more readily available on the West Coast and Southeast, where structural composite lumber may be more available in the Northeast. Similarly with treated products, it's best to talk to the dealers in market to understand what is available. The other costs that need to be considered are soft costs. These are costs that can be controlled by the specifier. First, there's no benefit in over-design. Remember, our job as a specifier is to specify the most efficient product that's strong enough to do the job intended economically. Over-specification doesn't necessarily make the job any better. Constructability. Consider the project. It may be more constructible to use wood versus steel, or a build-up SCL versus a full beam width. Don't specify products that are not readily available. If you look in a glulam book or even a steel beam book, there are hundreds of options that'll do the job, but specifying a product that isn't readily available only adds cost. A little research on product availability saves a lot of time and cost in the end. This also saves on review time and if substitutions are requested. To summarize, we've looked at the sustainability of wood used as a construction material, reviewed product basics of engineered lumber products, including proper design, specification, and installation of glue laminated beams and structural composite lumber. Introduced some new technologies, reviewed the constructability of SCL and glulam beams, and looked at some design options. With that, I'd like to thank you for your time and attention, and I'll turn this back over to Mary to see if any questions have come through.
Thank you, Bob. That was a lot of really great information. I appreciate it. I know that our audience appreciates it as well. We have had a number of questions come in. I have answered some of them if I had a quick, easy answer at my fingertips in the chat pane, and saved some for your list. So we'll go through a couple of those now. Another question we had was about SCL beams, are you allowed to rip those so that they're a shallower member? We talked about notching, but we didn't talk about actually just ripping the beam into a shallower member.
Okay, so let me first answer by noting that you're not allowed to rip glulam to shallower depths. We'll just go with that because I think we understand how the plies are different on the ends of the member, so that's why you can't rip them, because you know the different plies. But SCL, on the other hand, a little different in that the material is consistent throughout the depth of the member. You know, so cutting a deeper beam doesn't affect the reference design values, you know, the raw values, the F sub B's. You should check with your manufacturer, you know, before you say you're cutting a 14-inch to a 9.5. They should really match the strength properties. But if you really think about how structural composite lumber is made, even in LVL, they're quite often manufactured in billets that are 2 feet wide or even 4 feet wide. And essentially, when they come down to the shallower members, what they're doing is ripping those billets down to those depths. So structurally, you can. You just need to make sure you check your design values. So typically not a problem with this SCL, but not something you could do with glulam beams.
Great, thank you. We have a couple of questions related to built-up members. First, is it better to use a built-up beam or a solid beam that's an equal size and strength? And then second, if you are using a built-up member, how do you best connect it? Should it be screws or nails or bolts?
Well, the answer to your first question, I mean, it's a little challenging, and they both have, you know, positive attributes. A built-up beam is often easier to assemble. You can be built up in place, allowing the framer to more easily handle the product as compared to a wider section. You know, it's a lot easier working with lighter pieces. Whereas a solid beam, you may require additional equipment to handle it. You may need to bring a crane out or something like that with a solid beam. So the designer should really consider the conditions. If the beams are fully braced, as there typically are when installed on a floor where the joist brace the beam, you know, either choice is great. But if the beam is not fully braced, the designer will need to check that unbraced length may be different between a built-up member and a solid member, as the solid member may have a longer unbraced length when compared to built-up beams. So that needs to be checked. And then you're also going to need, if you do a build-up member, you're going to want to check the manufacturer's literature for how to connect that member, which actually brings us into the second question. When making a build-up, is it better to use bolts, screws, or nails? And again, the answer might be a little different depending on the application on which is best. They're often good. But you know, when you think about the wood being like a bunch of straws, it may be better to use a lot of smaller connections. So nails and screws may be preferable to bolts, where you're putting that big bolt through and trying to pull those straws apart. So that's why there's a strong preference for nails or screws right now. We do have some technical information for building up glulam beams that you can get off our website. I think it's technical topic 11 if you want to look up our glulam connection specific details. But for SCL, you're best going to the manufacturer, getting into their literature, their software that will provide some guidance and assistance on constructing a build-up member and help you select the appropriate connector in that application.
Great, thank you. Another question that came in is about treated products. Do treated products require special connectors?
It depends on the treatment a little bit. So if I start at that use classification 2 with the borate treated LSL, used in a dry use environment, that doesn't require any special connectors. But however, the preservative treatment in the metal connector industries recommend that metal connectors in contact with, say, ACQ treatment, should be hot dip galvanized in accordance with the ASTM standards. I think it's A553. For that product. So you need to really consult with the metal manufacturers and the manufacturers of the products and the treatments to find out what is the appropriate treatment for the connectors that should be used. It's not always an untreated fastener. It might be, if it's very harsh environment, it may be stainless steel. So I'd recommend checking with the manufacturers on what the appropriate treatment is.
Wonderful, thank you. We are running out of time. I am still getting up boatload of questions. If you hang on with us as I go through a couple of last housekeeping details, I will provide information to our entire field staff. We will review the questions that have been sent in and try to reach out to as many people as we can, but we do have people like Bob throughout the country that can help you if we didn't get to your question. So I do want to touch on 3 quick things related to a short survey, CEUs, and some upcoming webinars. We would really appreciate receiving your feedback. A QR code can be seen on your screen right now, and it can be scanned with your phone. It's also included in the handout, and a link will be sent to all registered participants shortly after the webinar ends. We really value your opinions as we plan these future webinars, so please take a few minutes and complete this. Also, don't forget to download the AIA or ICC Certificate of Completion from the form in the email that will be sent about an hour after the webinar ends. And finally, make sure that you're signed up to receive our APA update newsletter so that you'll be notified of our future webinars and updates to APA publications and standards. To receive it, all you need to do, starting from the home page of our website, is to click on Sign In the upper right-hand corner of the page. In the menu that drops down, simply select Register. From there, you will need to let us know what you'd specifically like to receive, which in this case is the APA Update newsletter. I should mention that if you have technical questions on any topic related to the use of engineered wood products, don't hesitate to contact the APA Help Desk at the address shown here. And like I said, Bob is just one of the many field staff we have throughout the country. These talented people are available to assist design professionals, builders, and code officials. Their individual contact information can be found on our APA website, www.apawood.org. Please feel free to reach out and take advantage of this resource. And as I mentioned earlier, a recording of today's webinar will be posted at apawood.org in a week or 2. And with that, I would like to thank everyone for attending. Have a wonderful day.